In our last video, we introduced complex variables and we discussed some definitions that will become useful throughout our discussion. And you saw some of my vacation photos along the way as well. So now we're going to focus on complex arithmetic and complex functions in this video. So essentially what we're doing in this chapter is just going back through arithmetic, algebra, trigonometry, and calculus and revisiting them now in light of complex numbers, variables, and functions to see how things are the same and how they're different. So we'll be doing that along the way in this video as well. And you can see kind of a long laundry list of different types of functions that we just need to get through to have that necessary background for doing the important things that we're really interested in. So let's go all the way back to grade school and redo addition, subtraction, multiplication, and division. I'm going to go through this very quickly because it's very intuitive. It's exactly what you would think in general. It is good practice to get us using complex variables and numbers and familiar with how to manipulate them. So let's start with a z1 and a z2. So two different complex variables. z1 is x1 plus iy1, z2 is x2 plus iy2. We're going to add them, we'll subtract them, multiply, and divide them. And the goal is going to be to separate out the real part and the imaginary part. So real part plus I times the imaginary part. So taking addition, z1 plus z2, well, that's x1 plus iy1 plus x2 plus iy2. You add the real parts, you add the imaginary parts, and you get the result. Exactly what you would think. Same thing with subtraction. Obviously, you just have a minus sign here, so you have minus signs everywhere throughout. Multiplication, so z1 times z2. Well, that's x1 plus iy1, quantity times quantity x2 plus iy2. And then you just multiply it like you would a normal set of factors. So you have x1 times x2, that's real. You have x1 times iy2, which of course is imaginary. You have iy1 times x2, that's also imaginary. And then you have iy1 times iy2. I times I is minus 1, so that's real. It's minus y1, y2. So there's the real part, and there's the imaginary part of the product. Now here's an interesting special case. If I have z and its complex conjugate, and I take the product, and I go through the same exercise, we'll actually end up with the real part being x squared plus y squared, and the imaginary part actually turns out to be 0. So this is handy because the product of z with its complex conjugate is always real. Not only that, it's equal to the square of the modulus of z. Remember, that's r, that's the distance from the origin to our point z. More importantly, the product is always real, and that's going to be helpful in division. So in division, if I have z2 over z1, obviously z1 can't be 0. So I have x2 plus iy2 over x1 plus iy1. Now the challenge is to get the I out of the denominator, because again, I want to write real plus I times the imaginary part for the result. So I need to get the I out of the denominator. So the way we do that is to multiply z1 times its complex conjugate in the denominator, and that will give us the real result, x1 squared plus y1 squared. Well, obviously, if we do it in the denominator, we also have to do it in the numerator. So we get this. Multiply it out, and we get the real part plus I times the imaginary part. Looks a little messy, but that's the quotient. Complex conjugates, these are exactly what you would think intuitively. So again, I'm going to run through these quickly. So we have the complex conjugate of the sum is the sum of the complex conjugates. The complex conjugate of the difference is the difference of the complex conjugates. The complex conjugate of the product is the product of complex conjugates. And same thing for the quotient. I've done the details for the first one to illustrate that that is the case, and I'll let you fill in the details for the other three if you're interested in that. Now, everything that we've learned about real algebra, trigonometry, and so forth is just a special case of this. It's the special case when the imaginary part of z, or z1 or z2, is equal to 0. So we're basically upgrading all of our real arithmetic and algebra to complex arithmetic and algebra. Sorry, I didn't realize there were more. So this is Banff. This is the actual town of Banff right here. So as I mentioned in the last video, this is what's different between national parks in Canada versus in the States. In the States, the towns are always outside the national park, whereas in Canada, they are inside the national park. So this is the town of Banff in Banff National Park. You may remember the Banff Springs Hotel picture. That's right down here overlooking the valley. Here's a golf course. It is just unbelievable. All right, that's enough. No more. All right, so let's talk about complex functions now. So we've talked about complex numbers, complex variables, how to add, subtract, multiply, and divide complex numbers and variables. And now let's look at complex functions. Again, our goal is going to be to separate out the real and imaginary parts in order to write it in that generic form. And as always, when imaginary part of z is equal to 0, that leads to the special case of real arithmetic, algebra, trigonometry, and so forth that we're familiar with. I'm sorry. I didn't realize there were more in here. So this is back to Lake Louise. Here's the actual lake here with the chateau down here. Right over here, actually, if you're familiar with the Canadian $20 bill, the picture on the back, this is Moraine Lake. It's down here. You can't see the lake, but this is Moraine Lake in the Valley of the 10 Peaks. It's just a beautiful sight, an amazing sight. Across the valley from Lake Louise, then, is this world-class ski resort. They have international competitions here. Now, if you look closely at this picture, you'll notice this is what happens when you teach your children to ski in the Midwest. So my kids had the misfortune of growing up in the Midwest where we don't have mountains of any note, and so skiing is very difficult to teach properly. You try to teach them to carve turns, but what they end up doing is just they spread the legs and they do the good old snow plow down the mountain. So this is two of my kids that are doing an excellent job of snow plowing. Horrible. It's embarrassing. I can't believe I showed you this picture. All right, trig functions. Again, I'm going to go through these relatively quickly, and actually this is why I've got my vacation photos in here, is because this material is very tedious. It's not terribly exciting, so put some vacation photos in here. So again, I'm going to go through this relatively quickly. The good news here is that there's nothing fundamentally different from what we are familiar with from the real case. So if you look at trig functions, sines and cosines, you can write sine of x is e to the ix minus e to the minus ix over 2i. Put in a z for the x and everything's the same. Taylor series is the same as what we learned for real functions. Same for cosine. Tan z is still sine z over cosine z, just like for real variables. So the good news is nothing changes. So all those trig identities that we learned and suffered through learning, they all still apply. So for example, we learned that cosine squared of an angle plus sine squared of an angle is just equal to 1. Well, that's true for z as well. So that's great. That really makes our lives a lot easier. Now, if you take the expressions for sine and cosine in terms of exponentials, if you multiply I times the first one and add the second one, you end up with this important result. So e to the iz is cosine z plus I sine z. If that's true for a complex variable z, it's also true for a real variable, say theta, and that's known as Eulers Formula. And if you've watched other videos, you may have seen me use Eulers Formula because it allows us to separate out the real part and the imaginary part of an exponential. So this is very useful. We use it all the time. That's Eulers Formula. That's where it comes from. So again, that results in our various ways to express z, either in Cartesian coordinates, x plus iy, in polar form, re to the I theta. They're all equivalent. Now let's take a look at the product of two complex variables, but now using polar coordinates. As I've said in the previous video, we can always pull out the Cartesian form or the polar form, whichever is most convenient. They're mathematically equivalent, and we're going to go back and forth, and we'll use the one or the other that is the most convenient for the moment. So let's just illustrate. We already did this in Cartesian coordinates. Let's do it in polar coordinates just to see what we get. So z1 times z2, well, that's r1 e to the I theta 1 times r2 e to the I theta 2. That's z1 and z2. So we have the product of the r's, r1 times r2. So the length of the product z1 times z2 is r1 times r2. So it's just take those two radial distances from the origin to the 2 points, multiply them together, and that gives you the distance to z1 times z2. Then the e to the I theta 1 times e to the I theta 2, that can be written as e to the I times theta 1 plus theta 2. So the argument of the product is the sum of the angles. So remember, the angles are from the positive real axis, so theta 1 plus theta 2. So that gives you the angle, the argument of the product. Similarly, then the quotient, z2 over z1, gives us r2 over r1, e to the I theta 2 minus theta 1. So then it's the difference. It's theta 1 minus theta 2 if it's the quotient. Okay, that's the last one. I'm sorry. Hyperbolic functions, won't go through this in detail, just here for completeness. Take a screenshot if you'd like and look through this. It's the same as what we had for sine and cosine in the sense that we can write it as exponentials, we can write them in terms of Taylor series, and so on. Like I said, last one, sorry about that. It is beautiful though, you have to admit. Exponentials, very similar, essentially the same as what we're familiar with real variables, so nothing new there. Polynomials, same thing. Okay, logarithms. Logarithms we need to take a closer look at because these are going to come up very frequently and we need to understand how they're treated. As I said in the previous video, we're told by our calculators, if it's a cheap one like mine, you can only take the logarithm of a positive real number. That's not true. You can put in any number and it does have a log. In fact, it has an infinity of values. Log of any number has an infinity of values. We need to be able to understand where those come from. So w is log base e of z, and if that's true, then e to the w is equal to z. Now you notice I'm going to use the log notation here, even though it's log base e. We engineers are used to using log for base 10, ln for natural log, which is a log base e. In complex variables, there's no need for log base 10, so we just generically use the log notation. So it is the natural log. All right, so e to the w is equal to z. So let's evaluate log z, and our goal is to isolate the real part and the imaginary part of log z. That's our goal. Now I could choose to use Cartesian coordinates, I could choose to use polar coordinates. I'm not sure which is going to be easier. Let's try polar coordinates here. I'll actually do Cartesian later on. All right, so I have log z, so that's the log of r e to the I theta. The log of the product of two things is the sum of the logs of the two things. So that's log r plus log of e to the I theta. Log base e of e to the something is the something. So log base e of e to the I theta is just I theta. So that's the real part, and that's the imaginary part. Great. Okay, so now log z, which is log r plus I theta, r is the same as mod z, so you can think of it either way. And then remember, theta is multi-valued, so that's theta 0 plus 2k pi, theta 0 being the principal argument between 0 and 2 pi, or minus pi to pi, whatever the 2 pi range we choose, and then plus any integer multiple of 2 pi brings us back to that same point. Okay, so that's our general expression, real plus I times the imaginary part of log z. We'll see how that's useful. Now, if we were to graph the values of log z on the complex plane, again, real axis and imaginary axis, it turns out that they're all along a vertical line. And whether there's a real value or not depends on whether the argument, whether the z, is positive and real. If it is, then there will be one value on the real axis and the others will be imaginary. If it's not, then none of these will be on the real axis. They're all imaginary. The location of this vertical line is log of mod z, or log of r, away from the imaginary axis. So let me make a few comments about what we've seen. So this is what I just said. And then what you'll notice is because logarithms are multi-valued, any other function, and we'll see that some trig functions, inverse trig functions to be specific, can be written in terms of logs. So any function that can be written in terms of a logarithm is itself multi-valued as well. And we'll see why that's actually a problem in the next video. Here is actually the derivation that we just did for real and imaginary part of log, where I use polar form, here using Cartesian. And you can see it takes a slide and a half or so to get at the same result. And this is a good thing to keep in mind. When you're doing a problem, sometimes it's obvious that you should use Cartesian, sometimes it's obvious you should use polar, sometimes it's not so obvious. So just try one. If things seem to be getting more complicated than you think intuitively that it should, then just try the other one. Maybe it'll be significantly easier, or maybe it's just a really messy algebraic manipulation that's required in order to accomplish it. So you always have these two options. Take advantage of that as you go along. All right, so let's do a simple example. Let's evaluate log of z, where z is I. So I is a point up here. It's on the imaginary axis, 1 unit above the origin. So the distance from the origin is 1. That's r, or the modulus of z. And the angle from the positive real axis is pi over 2, or 90 degrees. So theta 0 is pi over 2. So then log of z, z being I, is the log of mod z, which is 1. But log of 1, well, you put that into your calculator, it does get that right. That's 0. Plus I times the principal argument, pi over 2, plus 2k pi. So if we take this and write it in this fractional form, that's 4k plus 1 over 2 pi times I. So you can see that every value for any k is indeed imaginary. None of these values are on the real axis. They're all on this vertical line on the imaginary axis because they're a distance 0 from the imaginary axis, but none of them lie on the real axis. They're all imaginary. So fractional powers of z. This is also going to be an important one that we'll see come up periodically. So let's walk through this. So let's evaluate z to the power n over m. N and m are both integers. So this could be z to the 1 over 2, which would be the square root, 1 over 3, which would be the cube root. It could be z to the 2 over 3, whatever, fractional power of z. So let's write it in the following way using polar coordinates. Z to the n over m, I can write as e to the log of z to the n over m, because e to the log of something is just the something. Now let's write the log z to the n over m as n over m times log z. Remember, log of z to some power, you can bring the power out front. So that's n over m times log z. Then I can use the expression that we just obtained for log z. It's log of r or mod z, whichever you prefer, plus I times theta 0 plus 2k pi. So then we have e to the something plus something. So I can write that as e to the first something times e to the second something. So e to the first something, log r to the n over m. Now I've taken the n over m back and put it on the r as a power, times e to the I n over m theta 0 plus 2k pi, which of course comes from here. So now look what happens. So the e to the log r of n over m, well, that's just r to the n over m. And then I have this exponential. Now one thing that's interesting is that while k in general is any integer, positive, negative, 0, it turns out that k here goes between 0 and m minus 1, m being the denominator in our fractional power. What happens is all of the other values of k, negative values, and m and above, they all just give us back values that are already within this range. So what this means is if m, for example, were 2, then k would be 0 and 1, m minus 1, and there's 2 roots. There's 2 values. That's the square root. So something to the 1/2 is the square root. There's 2 values. If it's the cube root, then there's 3 values because m would be 3, and that would be k is equal to 0, 1, and 2. All right, so that's where we get those roots. So let's just do a simple example to see how this works out. So let's take z to the power 1/3, where z is 8. Now I've written 8 plus I 0, just to emphasize this is a complex 8. So z is real, it's 8 units to the right on the x-axis. But let's take z to the 1/3. If I were to ask you today, what's the cube root of 8? Most of you, and if you put it in your calculator, most of your calculators would say, well, of course it's 2. 2 times 2 times 2 is 8. That's the cube root of 8. Well, that's true. That is one of them, but there should be 3, because this is z to the n over m, where m is 3. So there should be 3 values, and in fact they are. But the other 2 values are complex, as we'll see. All right, so the way we do this is my z is 8 units to the right. So what is mod z? Well, that's just 8. That's the distance from the origin. What is the argument of z? Well, that's just 0 because it's on the positive real axis, so the angle from the positive real axis is 0. So theta 0 is 0. M is 3, n is 1, so k goes from 0 to 1 to 2. So there's 3 values, which makes sense. This is the cube root. There should be 3 values, and indeed there are. So from the expression that we just had for the fractional power of z, z to the 1/3 is 8 to the 1/3, which of course is indeed just 2, times e to the I 1/3 times theta 0 plus 2k pi. I'm going to write that as cosine of pi over 3 plus I sine pi over 3. And now k being 0, 1, and 2 corresponds to theta being 0, 2 pi, and 4 pi. So let's just remind ourselves of some of these cosine and so let's just remind ourselves of the necessary sines and cosines. So cosine of 2 pi over 3 is minus a half. Sine of 2 pi over 3 is root 3 over 2. Cosine 4 pi over 3 is minus a half. And sine of 4 pi over 3 is minus root 3 over 2. So we take the 3 values. First, take theta is equal to 0. Cosine of 0, of course, is 1. Sine of 0 is 0. So that's why we just get 2. That's the real result that we would expect. Then we take theta as 2 pi. Theta is 2 pi, so that's cosine of 2 pi over 3. Well, from here, cosine of 2 pi over 3 is minus a half, cancels with the 2, and we have minus 1. Sine of 2 pi over 3, sine of 2 pi over 3 is root 3 over 2. So this becomes root 3 over 2. The 2's cancel, and we have plus I times root 3. Then finally, for theta is equal to 4 pi, put that in, cosine of 4 pi over 3, sine of 4 pi over 3. We get a minus 1 again from the cosine, and from the sine we get a minus root 3. So you notice that the other 2, other than the real value, the other 2 are just complex conjugates of each other. So there are indeed 3. 1 is real. The other 2 are complex, but they're complex conjugates of one another, and that's typical. So here's the point. Again, obviously if I take 2 times 2 times 2, I indeed do get 8. But equally accurately, if I take minus 1 plus I times root 3 times itself 3 times, I will also get 8. Likewise, I take this times itself 3 times, I will also get 8. So mathematically, there's no reason to favor this one. Now, if this is an equation that gives me the number of sheep that I expect to return to the pen at night, well then of course I expect a real number and I would throw these away. But mathematically, these are all equally valid results. Okay, inverse trigonometric functions. Again, not going to go through the details here. So these are sine to the minus 1, cosine to the minus 1, or arc sine, arc cosine. But let me just illustrate some interesting results. So you'll notice here I have inverse cosine, inverse tan, sinh, cosh, tanh. They are all written in terms of logs. So what that tells us is because the logarithm itself is multivalued, that means that all of these inverse trig functions are also multivalued. And again, that's going to be important when we consider the calculus, the analyticity of these functions.